In this video, the instructor is explaining the concept of the optical path length in a numerical method instead of working with equations that contains only letters. Okay, and I have found it useful for you to watch this video in order to understand the concept of optical path length, and I will let you watch this video, and if you have any questions you can ask later.
I want to first consider that we have a block of glass in air, and this glass is 1 meter thick and has an index of refraction of 1.50. And if we wanted to know how long it would take for a ray of light to travel from one end of the glass to the other, we could use our formulas. Velocity equals distance over time. And in this case, we want to solve for time. How long does it take for that ray of light to travel through? And so we could rearrange to T equals D over V. And we are given the distance of 1 meter, but in order to find the velocity, we'll have to use the index of refraction. And we know that N equals C over V. And if we want to solve for V, we would say V equals C over N. And in this case, the velocity of the light in the glass is going to be 3 times 10 to the 8th meters per second divided by 1.5. And that would give us a velocity of 2 times 10 to the 8th meters per second. And now we can use our value that we just found for V and plug that into our velocity equation up here, which is solved for T. And T is going to be equal to the distance of 1 meter divided by 2 times 10 to the negative 8th. 2 times 10 to the 8th meters per second. And our amount of time that it takes for that ray of light to travel through will be 5 times 10 to the negative 9 seconds. You could also take this term that we found is equal to V and plug that into your equation here. And so now we could say that T is equal to D over C divided by N, or if rearranged properly, it would be dN over C. And for example here, the distance of 1 meter times the index of refraction of 1.50 divided by the velocity, the speed of light, 3 times 10 to the 8th meters per second. And you would find the same result for the time of that ray of light to travel through, 5 times 10 to the negative 9 seconds. And this term here, the dN, is equal to the optical path length. The definition of the optical path length being the distance that light would have traveled if it was given the same amount of time in air. And we could look at our example and say that if light in air, we'll consider this ray in air, if that light, since it's in air, is traveling 3 times 10 to the 8th meters per second, and we know we're going to use the same time value, 5 times 10 to the negative 9 seconds, we could say that 3 times 10 to the 8th meters per second is equal to the distance we're trying to find, how far could it travel, divided by the time that we're given, 5 times 10 to the negative 9 seconds. And you would find that given the same amount of time, a ray of light in air could travel 1.5 meters. Alternatively, you could use just our optical path length formula and multiply d times n. And our distance in the glass was 1 meter. The index of refraction is 1.50. And the optical path length for the ray of light in the glass is 1.5 meters. Meaning that if that ray of light had been in air and it was given the same amount of time, it could have traveled 1.5 meters.
Of course, in your books, in page 302, you have a good explanation, a good general explanation about the optical path difference or optical path length and how it differs from the geometrical path length. But I prefer also to take a look about this treatment, this numerical treatment for the same concept in order to enhance the idea.